rotational motion. Now I suggest you buckle up because this is a doozy. The Discord server is there if you need it. Let's get right in. What is rotational motion? Okay, rotational motion is the motion of wheels, more or less, like the wheel of your car, or the rotation of my hand, my fist, like this. That is rotational motion. It is motion of things about a common axis. So when we covered circular motion or orbital mechanics, that would have been classified as rotational motion. It's motion that is in a circular path around a center. First of all, rotational motion is going to be very analogous to linear motion. So more or less, the concepts, laws, and equations that apply to linear motion will generally apply to rotational motion, of course, with different quantities. Okay? When we talked about position in linear motion, translational motion, position was defined as x, a linear position. In the case of rotational motion, we're going to define position as theta. Theta being an angle, okay? If you are moving in circular motion about the center, then your position on the circle can be defined using an angle theta, okay? And if you remember from the unit circle from pre-calc, and the angle 0 is always defined as the rightmost point in the circle, as angle 0, and positive angles increase counterclockwise, okay? Meaning at here you would be angle 0, here you would have pi over 4, here you would have pi over 2, all the way on the left is pi, bottom is 3 pi over 2, and then back here is 2 pi. Your position in your rotation is identified by your angle theta in radians, okay? So in linear motion, we expressed velocity, linear velocity, as v. In rotational motion, we're going to express it as omega, the W-looking thing. Omega being denoted as angular velocity. All right, and as we discussed in the previous video about oscillatory motion, your angular velocity is in units of radians per second, similar to how velocity was in units of meters per second. Position was in units of meters, theta is in units of radians. So in much the same way that your position is defined by an angle in radians, your velocity is defined by how many or how much angle you travel through every second. Again, we see angular velocity being the rate of change of theta. And of course, the relationship we learned back in kinematics still holds. How position is equal to the area under a curve of a velocity time function, theta is equal to the area under the curve of an angular velocity time function. Okay, and then down here, if we go one step further, we have linear acceleration a, and we have rotational acceleration alpha. It's kind of difficult to draw an alpha that doesn't look like an a, but it's in your best interest to learn how to make them distinct. The way I draw the linear acceleration a is I do it in one pen stroke like this, and the way I draw the angular acceleration alpha is I draw like a little open circle like this, and I connect it down like that. And maybe we could add a little curvature up here, so that it's very obvious that these are not the same quantity. Angular acceleration alpha, linear acceleration a. And also, when we were dealing with linear motion, we defined our inertia as mass, okay? I don't believe I've adequately described what inertia is. Inertia is the resistance an object has to start moving, okay? So this marker is going to have a lot less inertia than this laptop. Reason for that being, as you might be able to tell, it is a lot easier to move the marker and it's a lot harder to move the laptop, okay? Inertia is how difficult something is to initiate into motion. In linear motion, your inertia is the same as your mass. An object with greater mass is going to be more difficult to accelerate and more difficult to move. So the linear variable for inertia is mass. The angular variable for inertia is I, which means rotational inertia, okay? Rotational inertia is quite a bit more complex than just saying mass. Rotational inertia being so complex is it's deriving values for rotational inertia is largely a concept you will only see in physics C mechanics because it requires calculus. So the rotational inertia that we'll be seeing here in the algebra course, there's generally two types, okay? Type A is when you have a solid object that has the rotational axis going through it. Like, let's say I have a solid sphere, okay? Solid sphere, meaning I've got a ball and it's not hollow. The sphere is solid, meaning that there is mass all throughout it. Think of like a cue ball. A cue ball would be an example of a solid sphere, where something like a tennis ball would be the example of a hollow sphere. Okay, we're just going to look at a solid sphere for now, such that there's mass all throughout the center, okay? And if I were to rotate a solid sphere about an axis of rotation that goes through the center of the sphere, like if we looked from the top of the sphere, the center of rotation would be going directly through the middle, as my marker is. If that were the case, your rotational inertia I would be given to you in the problem. It would be given to you. And the rotational inertia I will always be defined as some constant c times the mass of your object times the radius of the object squared. So this is the general formula for rotational inertia. Some unknown constant c, unknown, times the mass of your object times the radius of that object squared. The reason that that in type A your rotational inertia would be given to you in the problem is because you cannot determine C without calculus. So because this is an algebra class, they're just going to give you C. They're just going to hand it to you. They're just going to say, this is your rotational inertia. You have a different type of problem, type B, where you have an axis of rotation and you have some particle, some point, that the rotational axis is not going through that point. And the reason I describe it as a point is because this largely only works for uniform masses, like spheres, like balls, like particles, okay? So if you find yourself in a situation where you have an axis of rotation that isn't going through your object, then your rotational inertia equals 1 times the mass of the object times the radius of rotation squared. In this example, your constant c is 1, okay? But in this example, radius is not asking you for the radius of the shape. It's asking you for the radius of rotation. It's asking you for the distance between your rotational axis and your particle, okay? In this case, the rotational axis happens to be at the center of our sphere. So the radius of rotation is from the center of the sphere to the edge. Make note that the radius of rotation is what is denoted by r, not the radius of your shape. Sometimes they will be the same thing. In this case, they are not. Okay? So remember these two cases. Either you're given rotational inertia, or you're given a situation like this in which you are expected to know that the rotational inertia equals mass times rotational radius squared. So now that we've identified the variables that we're going to be dealing with in this case, we can move on to the kinematic equations, okay? Now, kinematics was our first unit here in AP Physics 1, and the same analogous equations can apply. When we covered kinematics in Unit 1, we were looking at equations such as your x position equals your initial x position plus your initial velocity in the x direction times time, plus your acceleration times time squared over 2. Okay, that was one of the kinematic equations we covered back in Unit 1. All right. The kinematic equations for rotation are exactly the same. You just need to sub in the new quantities. So theta equals theta naught plus omega naught t plus alpha over 2 t squared. Same exact equations, just sub in your new quantities, okay? So despite it being so similar, you are still given your kinematic equations for rotation on the equation sheet. You are given theta equals theta naught, this equation we just derived out, and you are given omega equals omega naught plus alpha t. Now, there was one more kinematic equation that we covered in the beginning of the year, and that was your velocity at point x squared equals your initial velocity in the x direction squared plus 2 times the acceleration in the x direction times your change in x. Okay? That was the linear equation. And similarly, you can convert this to angular form by simply switching out the linear quantities for angular quantities. I'm not going to rewrite that out, you just saw the transformation done right here. So, moving on from kinematics, the next unit in the Physics 1 course was dynamics. And in dynamics, we introduced forces, we introduced acceleration. And in rotational motion, there is also an analog to force. In rotational motion, we have torque, denoted as such, like a squiggly T. In rotational motion, we have period, and we have torque. Okay? I do not want to be guessing. If I'm your grader, I don't want to be guessing which one you meant. Okay? If you write torque like a capital T like this, that's not torque, that's period. Learn how to write your Greek letters. So what was the central concept of the dynamics unit? It was Newton's second law. What was Newton's second law? That was force equals mass times acceleration. All right, so what is our rotational analog for force? That is torque. What is our rotational analog for mass? Also known as inertia. That would be your rotational inertia I. What is our rotational analog for acceleration? Angular acceleration alpha. Oh, looky there. Now we have Newton's second law for rotational dynamics. Also given to you on your equation sheet, if I am correct. Yes, it is given in the same form on your equation sheet. Angular acceleration equals net torque over rotational inertia I. That is how it is given to you on your equation sheet. Torque is also present in one other equation on the equation sheet, and that equation stipulates torque is equal to radius times force times sine theta. Let's break down what this equation is telling us. Okay, so let's understand it in reference to this. Torque is equal to our rotational inertia times our angular acceleration. It means if we have an angular acceleration, it means that there must be some torque being applied to the wheel. And if we apply some net torque to the wheel, it means that there is going to be an angular acceleration induced upon the wheel. Okay? So, how do we induce a torque? That is what this equation is explaining to us. This equation defines the effects of torque. This equation defines the causes of torque. All right, so what causes torque? If I were to give you the age-old example of a nut being tightened by a wrench, it's a horrible wrench, I know, but whatever. We have our center of rotation here, because the nut is rotating around its center shaft. And as we try and turn that nut, our hand is going to be gripping it right here and trying to pull it downwards, okay? This equation says that torque is equal to the force applied multiplied by the radius it is applied at, multiplied by the sine of the angle between those two vectors, okay? Let's draw this diagram out with just lines to make this easier. This center is our nut, and this line right here is our wrench, okay? If my hand is gripping the wrench right here, I am applying an applied force downwards to tighten the nut, okay? I'm applying that force onto the wrench, and I'm applying that force a distance r away from the center of rotation, okay? The distance between the point at which the force is applied and the point at which you are rotating around, that distance is going to be your r. The force applied to the wrench, the force applied at that distance, is going to be your force F. Sine theta is going to be the angle theta between the two vectors, okay? Because remember, force is a vector, radius or distance is a vector. So in this case, the force applied and the radius vector are at exactly 90 degrees. Sine of 90 degrees, or sine of pi over 2, is 1, meaning that maximum torque is applied when the angle theta is 90 degrees, okay? If instead the force were to be applied at a different angle, then theta, in this case, is decreasing, sine of theta is decreasing from 1, and now we would be dealing with the radius vector times f times, let's say, sine of 70 degrees in this case, which would be less overall torque than what would be applied if the force vector and the radius vector were perpendicular. So if you want to apply maximum torque, you want to apply a force at 90 degrees. Given that these two equations are in terms of our torque, we can say that the angular acceleration times our rotational inertia of a rotating body is equal to the radius at which a force is applied times that force times the sine of the angle between them. We can then make that derivation from these two, okay? And that is a derivation that you are going to need to make to answer the great majority of rotational problems that you'll encounter. So let's, in the case of free body diagrams of torque, there's an interesting nuance that is introduced, okay? So if I were to be given a rod, let's say like this, and I were told that it has a uniform density means it has the same density everywhere, that should immediately tell you that any object with a uniform density, the center of mass is directly in the center of the object. So let's say I have a rod that is allowed to pivot because it's connected to a hinge connected to this wall. And let's say it has a string holding it right here, okay? And you are told that the rod is held in place in this position, okay? Now you'd be asked to draw a free body diagram of the rod. In the case of rotational analysis, the point on the rod where you draw your arrow is significant, okay? So, for example, you would need to draw the force of gravity acting on the center of mass, okay? So you would need to draw your force of gravity as an arrow originating at the center of mass and pointing downward, okay? For the case of the normal force, because the wall is exerting a normal force onto the rod because the two are touching. Okay, so the normal force must originate at the point of contact and point in its respective direction. Okay? You see what I'm starting to say here? The origin point of the applied force in your free body diagram is important now. Okay? You will get points taken off if you draw normal force like this. And that's important because on the free body diagram parts, it's all or nothing. If you make one silly mistake, you get the entire free body diagram wrong. The grading system on these FRQs is very rigid and it's very all or nothing, okay? There are 3 FRQs and each subpart is very lengthy, okay? So an example of one of the FRQs would be calculating the center of mass with calculus, a topic we covered in Unit 2, okay? You would get 1 point for setting it up correctly. You would get 1 point for setting up the calculus correctly, and you would get 1 point for the correct answer, all right? So if you didn't know what equation to use and you couldn't get the first point, you can't get the other 3 points, and you just lost the entire subpart because you didn't know what equation to use. That's my point. There are very few points to be earned, and because there are very few points to be earned, there are a lot of qualifications you need to get each point. Back to this, okay. The last force we need to draw is the force of tension in the string. Force of tension in the string would originate from here and would be pulling back up in this direction. And we can see here that if we resolve the string force into components, warning, never ever ever draw components on your free body diagrams. That is getting the whole free body diagram wrong. I'm doing this off to the side, if you'll notice. If I were to resolve the string force into components, I could have a horizontal component that opposes the normal force, and I would have a vertical component that opposes the gravitational force. Such that since the directions of all of my forces are balanced, and the magnitudes are all balanced, I am in translational or linear equilibrium, but in order to calculate rotational equilibrium, I need to balance torques, okay? So first of all, we know our center of mass, and we have a hinge here. If this rod were to be released from rest, around which axis would it rotate? Would it start rotating around the center of mass, or would it start rotating around the hinge? It'd start rotating around the hinge. Okay, so this right here would be our axis of rotation if it were released from rest. Okay, so let's understand the contributions of all our forces. The net torque is equal to the sum of all the individual torques. Okay, first of all, the radius vector would be in what direction? The radius vector would be in the same direction as our normal force, okay? And since the radius vector and the normal force vector are in the same direction, the sine of that angle theta is 0, therefore there is 0 torque contribution from the normal force. Therefore we can eliminate that from consideration, okay? The torque applied by the string force must therefore completely balance the torque applied by the gravitational force, okay? So, since we know the rod is not moving, we can say that the net torque equals 0, and we also know that the net torque is equal to the torque provided by the string plus the torque imposed by gravity. Therefore, we can say that the magnitude of the torque in the string is equal to the magnitude of the torque applied by gravity. And that would be a useful derivation to make if, for example, you were asked to solve for the tension force in the string, given the mass of the rod. And of course, to calculate gravitational force, you would just do mg cross r. You'd be given the radius, you would be given the length of the rod. You'd be given the total length of the rod. And it would be up to you to understand that since the center of mass is in the exact center, the radius at which the force of gravity is being applied is a distance L over 2 from the center of rotation. So you would need to make that distinction, okay? That the total rotational inertia, I sub tot, is equal to the sum of all the rotational inertia about the same principal axis. We'll discuss that in just a moment, which is also equal to the sum of all of the masses in the system multiplied by their radius squared from the distance of rotation, from the axis of rotation. Okay? So let's discuss this part first. The total rotational inertia is equal to the sum of all the component rotational inertias. This statement is only true if all the component rotational inertias are with respect to the same axis, okay? So if I have a wheel rotating around its center, and I calculate its rotational inertia, I'm going to call it I sub 1, and I have a second wheel with it spinning around its center, and I calculate its rotational inertia I sub 2, and I place the second wheel onto the first, such that now I have one wheel on top of the other, and they are both rotating around the same center axis. In that case, then the total rotational inertia of the new combined wheel is equal to the rotational inertia of 1 plus the rotational inertia of 2. Okay? If I placed the second wheel onto the first, but I were to place it over here, then this would no longer be true, because we have a different axis of rotation for both components. Okay? Now let's move on to the second part. Let's say I had a tray, circular tray of negligible mass, and we're going to discuss the importance of that in just a moment. Let's say the tray has negligible mass, and on top of that tray are 3 heavy balls. Okay? And let's say that the tray is rotating around an axis right here. Okay? I want to calculate the rotational inertia of this system, of this conglomerate of objects. Okay? Therefore, I would need to sum up the component masses multiplied by their radius from the center squared. Okay? So first off, let's consult the main dish. Okay? The dish has negligible mass, so therefore it does not contribute significantly to our rotational inertia. Next, let's consider this ball in the top left. Let's call it a mass of 4 kilograms. And it has operating at a radius from the center of 0.2 meters, 20 centimeters. Okay? The other ball has mass 2 kilograms, operating at a radius of 40 centimeters, 0.4 meters. And the final ball on the bottom has mass 3 kilograms at a radius of 30 centimeters. Or 0.3 meters, I should write. Okay? So therefore, I would take the first contributor, I would calculate its moment of inertia. There are 2 words for this quantity I. It is called both rotational inertia and moment of inertia, and I'm going to use those words interchangeably. So I'm going to take 4, multiply it by 0.2 squared, and that is going to be the rotational inertia contribution from ball 1. I'm going to take 2 times 0.4 squared, that's going to be the rotational inertia contribution from ball 2. 3 kilograms times 0.3 squared, that's going to be the rotational inertia contribution from ball 3. And I take I1 plus I2 plus I3, and I sum them together to get the total rotational inertia. Now you will notice this process here looks a lot like that. The reason this is true is because we are all calculating rotational inertia with respect to the same center of rotation, okay? Because all of our radius calculations are done with respect to the same center of rotation, okay? So that's how we would calculate rotational inertia for a system of a finite amount of participants, a finite amount of blocks. Now, one note, I did not draw this diagram to its fullest accuracy, okay? The distance calculation should not be done with respect to the edge of the ball. The distance calculation is between the center of rotation and the center of mass of the participant. Okay, I wanted to clarify that because my diagram here doesn't show that, but know that it is not the distance between the ball and the center, it's the distance between the center of mass and the center. One more thing before I let you all go, it's the parallel axis theorem, the final equation of rotational kinematics that we have on our equation sheet is this, okay? What does this mean? It means that, let's say we have a circle that would otherwise be rotating around its center of mass, and when the circle is rotating around its center of mass, it's going to have some moment of inertia I1, okay? Now, if instead we wanted to rotate the circle around a different axis, let's say we wanted to rotate the circle around its edge such that it was spinning around and around like this, around this center of rotation, then it would gain a new moment of inertia, I prime, such that I prime, the new moment of inertia, equals the moment of inertia at the center of mass, which we defined as I1, plus the mass of the disk, or the mass of the object, multiplied by the radius squared, wherein the radius is equal to the distance between your center of mass and the new axis you are rotating around. Pretty simple equation.